to the power half will give you centimeters. Okay, so that radius will come out in centimeters. Okay, so R comes out to, the radius comes out to 4 centimeters essentially. Okay. So that's the radius of the cup. Okay. The second problem says a trash compactor can compress its contents to 0.35 times its original volume. Okay, so the final volume is 0.35 times the original volume. Neglecting the mass of air expelled, by what factor is the density of the rubbish increased? Okay, so the initial density is the mass times initial volume, and the final density is the mass is the same and divided by the final volume. Okay. So the final density is, and the final volume is 0.35 times the initial volume, and so that is 1 over 0.35 is and that's 2.86 times the initial density. All right, so you guys have seen those crushed cars that go on semi-trucks and stuff like that? Okay, so the density of those cars as sort of, if that's the volume that, if they were crushed and their volume decreased to 35% the initial volume, their density would increase by that factor. Okay. All right, a dam is used to hold back a river. The dam has a height of 12 meters. 12 meters is roughly twice the height of this room. Okay. And a width of 10 meters. 10 meters is roughly half the width of this room. Okay. So assume that the density of water is 1,000 kg per meter cube. Determine the net force on the dam. Okay, so here's the problem. So you want to find the total force on the dam. Okay. All right. The pressure of water at a depth, you saw the formula was P naught. Oops. The pressure at a depth is P naught. P naught is atmospheric pressure plus rho GH. Okay. H is the height of the water or the depth of the water. Okay, so the pressure is increasing. All right, when we calculate the force, well, there's also atmospheric pressure in this direction. Okay, so the net pressure is this pressure minus that pressure, which is this pressure minus P naught. Okay, so this is P and this is P naught. Okay, so it's the gauge pressure that's the pressure acting, which is P minus P naught equal to rho GH. We'll call it the net pressure. The net pressure. Okay. All right, so now the force on this strip of the dam is the net pressure. So the force on that thing is the net pressure times the area of that thing. The area of that strip. Well, what is the area of that strip? It's the width times dy. So dF, the force on that strip, is the net pressure times the width of the dam times the thickness of that strip. And now we want to add up all these forces to get the net force on the dam. Okay. So the total force on the dam wall is the sum of all these forces dy, and dy goes from 0 to the height of the dam. All right, so the pressure is 0 to h rho gh dy. What is h equal to? H is equal to h minus y. So the force is equal to 0 to h rho g h Okay, this is a constant, so when you integrate, all you'll get is rho g h y, and the second term will be rho g, and the integral of y is y squared by 2. And then the limits are 0 to h. Okay, so this first term will become h, so rho g h squared minus rho g h squared by 2. So this is rho g h squared by 2. All right, now let's write it this way. I kept forgetting to do the weight here. I mean the width here. All right, so this is rho g h, half rho g h times h times w. All right, so the reason we are doing it this way is so the net force on the wall is this guy, and the reason I'm writing is h times w is the area of the wall. This is the gauge pressure at depth h. It's this half is the average pressure on the gauge pressure on the wall. So the force is the average pressure times the area of the wall, and that makes sense. Okay. So this is the average pressure. Yep.
Did you get rid of that term because it was 0 for the first point?
I'm sorry?
Um,
What line?
the second line from the bottom.
This one?
From the bottom. And then from there to the next equation, you got rid of that first term.
No, 1 minus a half is a half.
Right.
Mm-hmm. Okay. So this is the average gauge pressure, and this is the area of the, okay? So the net force is 1/2 rho GH times the area of the wall. Okay? That's the net force on the dam. Remember, the pressure is increasing, and so all you do is calculate the average pressure. The pressure is increasing linearly, and so it's just the average pressure times the area. Okay. All right, this problem says assume bicycle tires are perfectly flexible and support the weight of a bicycle and rider by pressure alone. Calculate the total area of the tires in contact with the ground if a bicycle and rider have a total mass of 80 kgs. And the gauge pressure in the tire is 3.5 times 10 to the power 5 pascals. That's 1 atmosphere. So the pressure in your gauge pressure in your tires is 3.5 atmosphere. In your cars, the pressure is gauge pressure is 2 atmosphere. So in your cycle tire, the pressure is greater than in your car tires. Okay. Why is that? The car has to bear a larger weight. Okay, so you'll see the answer to that in a second. And okay, so we'll get to that in a second. Okay, so there's the pressure inside the tire, that's the absolute pressure, and there's atmospheric pressure, okay? So that pressure is pushing down and atmospheric pressure is pushing up. So the, okay, so, okay, so here's the force of gravity acting on it, which is pushing, okay, the force of gravity, and the ground is pushing back with an opposite force. Okay, so there's the force of gravity. And the ground, the normal force is pushing with the force of gravity. And so this piece, on this piece, the ground is exerting a force equal to the force of gravity. And so the air, the force of the air has to act in that direction. So that's the piece of the tire that's in contact with the ground. So those are the forces. And what is the force of air? It's this pressure, and there's atmospheric pressure acting this way. So the force of air, which needs to equal mg, is absolute pressure minus gauge pressure times the area, this area that is in contact. Okay. This is the gauge pressure, which is that. So the gauge pressure times area equal to mg. That's the weight being supported. All right, so this equation has a, so this is the pressure, gauge pressure of air in your tires. Okay. All right, this is the weight you're supporting. Now in a road bike, when you're riding a road bike, this is your weight. What are road bike tires? They're very thin. Why are they thin? I'm sorry?
They support less weight.
No, you are riding the same rate, yeah.
Less friction with the ground.
Less friction with the ground, and they're aerodynamic. Okay, so this area is less. The area of contact with the ground is less. So the pressure in those racing tires has to be greater. Okay. In a mountain bike, this area is greater, so the pressure is less. Yeah. Now let's come to semi trucks. Semi trucks, you have to support a lot of weight. You can't arbitrarily increase the pressure in the tires. So what do? More tires. So you got to increase. So that's why you have to have more axles. Again, that's how you increase more area. The heavier the vehicle, the more tires there will be to increase the area. Okay. All right. So what is it that we're trying to find? The area. Okay, so what I'm going to do is into 10 to the minus 4. I'm going to take 110 and multiply that by make that 35, 10 to the 4, and then when that comes to the top, that becomes 10 to the minus 4. And you'll see in a second, this area will come out in meter square, 80 into 9.8 divided by 35. And this is centimeter square. Okay. So the area that's about 25 centimeters square, which is 5 inches by 5 inches. So about this much area. I mean, 5 centimeters by 5 centimeters, 2 inches by 2 inches. So that's how much area of your tire is in contact with the ground. And that's with both the tires. Okay, we just drew one tire, but that's a combination of both the tires. Okay. So again, you want to support more. If you want to support more weight, you can increase the pressure in the tires. The pressure, if you keep increasing the pressure, your valves have better be good. Okay. And there's only so much pressure you can increase, and so then you'd have to increase the area in the tires. When there's less area in contact with the ground, then your rolling friction is less. Okay, so when you fill, and you've experienced this when your tires are low with air, when the pressure is low, more area is in contact, there's more friction, and it's harder to ride the bicycle. What force must be exerted on the master cylinder of a hydraulic lift to support the weight of 2000 kg car resting on a second cylinder? The master cylinder has a 2 centimeter diameter, and the second cylinder has a 24 centimeter diameter. Okay. So So this is the input force, and the diameter here is 2 centimeters. This is called the master cylinder. This is also called the slave cylinder or the second cylinder. And here's the output force, and this is where you're supporting the weight. Okay. So what you want is this output force to balance the weight of the car. Okay, so what you want is F out times area out this is the area of the cylinder, okay, should equal, oops, no, this, the output force is the pressure outside times area out should equal mg, the weight that you're supporting. Okay, the weight of the car needs to be balanced by this output force, which is the output pressure times the area out. Okay. Okay, so what you saw was input force. Mr. Pascal says okay, what Mr. Pascal says, if you increase the pressure in an enclosed fluid at any location, you increase the pressure by that much, input force divided by input area, you increase the pressure at this point by that much, that pressure is transmitted to every point undiminished. That pressure increases every point by that much. So this is equal to the output force divided by area out. Okay. So the output is all right, so we're going to put that in here. Okay, so output area times input area, input force equal to mg. Okay, and what they're asking us to find is what force must be exerted, so they're asking us the input force. So the input force equal to that's the weight of the car. Okay. Okay, input area is pi r input square. Output area is r output square. All right, so they tell you the diameter is 2 centimeters, so the radius is 1 centimeters, input radius. The diameter is 24 centimeters, so the output radius is 12 centimeters. So this guy is 1/12. So this is 1/44 mg. Okay, so you see the input force is 1/44 the weight you're lifting in this device. So the output force is 1/44 times the input force. So this guy is a force multiplier. You put in a 1 pound force, you get an output of 144 pounds. Okay, so that's what this thing is doing. So if you want to lift a 1,440 pound object, all you have to apply is a 10 pound force. Okay. That's what that does. So all you see is how to easily calculate. You divide this radius by that radius, and if the ratio is 10, the force multiplier is 10 squared, 100. You take the radius, ratio of radius, and then square it, and you get the, so take the radius ratio and multiply, square it. Okay. All right, so you saw that you increase the pressure, so you apply a small force in a small area, you increase the pressure by a certain amount, and then on a wider area, the output force is much larger. Okay, so we'll do this. Okay, so again, the force on the a larger area is larger. Okay, so we're going to apply this thing on a special problem. Okay, so all right, so in this problem, a host pours the remnants of several bottles of wine into a jug after a party. The host then inserts a cork with a 2 centimeter diameter into the bottle, placing it in direct contact with the wine. So this is completely filled with wine. The host is amazed when the host pounds on the cork into place, and the bottom of the jug with a 14 centimeter diameter breaks away. Okay, so this radius is 1 centimeter, this radius is 7 centimeters. 7 square is 49. So whatever force you apply here, the output force is 49 times that. And this bottle breaks. So that's what's going on. Did you guys understand that? Okay. So again, this is again a force multiplier. So we are applying Pascal's law. Okay. So this is the pressure you increased at this point, and that pressure is transmitted undiminished. So F2 over A2. So F2 is A2 over A1 times F1. Okay, so pi R2 square R2 is 7 over 1 square. Okay, so you apply a force of F1 here, and what you get, F2 at the bottom of the bottle is 49 times that of the input force. Okay. When will this happen? If there is no air in the thing, it has to be completely full of liquid. Why can't you have air? Air compresses. Okay. All right. And yeah. So if a person's body has a density of 995 kg per meter cube, see this density is less than the density of water, which is 1,000 kg per meter cube. So you should float. This person should float. Okay. What fraction of the body will be submerged when floating gently in fresh water? In salt water with a density of that much. Okay. You guys have seen pictures of people floating in the Dead Sea. Okay, so the Dead Sea has a fairly high density. Okay. The density of the object divided by the density of fluid equal to volume displaced divided by volume of the object. Okay, so when something floats, the density of the object has to be less than the density of the fluid, and then the displaced volume will be less than the total volume. Okay, so that's the volume of the object. Okay, so in part A, this is 995 kg per meter cube. and fresh water, the density is 1,000 kg per meter cube. So the displaced volume is the volume that is submerged divided by the volume of the object. Okay, so 0.995, and if you multiply so in part A, 99% of the object is immersed. This is 99.5%. Okay, so if you don't panic, you can stick your nose out. It'd be good. Yeah. And be in salt water. So in salt water, this is 96.9% of you're immersed. Okay, so if you haven't seen this, see, so the density of water in the Dead Sea is quite high. The reason it's called the Dead Sea is it's got an inlet and all the water is evaporating, and the water is getting saltier and saltier. Nothing lives in there. Yeah. Calculate the buoyant force on a 2-liter helium balloon. Given the mass of the rubber in the balloon is 1.5 grams, what is the net vertical force on the balloon if it is let go? Okay, so here's a helium balloon. Oops. The volume is 2 liters. Okay, and okay. And the buoyant force. Okay. So the buoyant force is equal to what? What is the fluid that is displaced? It's the weight of the fluid that is displaced. What is displaced? Air is displaced. Okay, so it's the weight of fluid, in this case air, that is displaced. Okay, so that is the density of air times the volume of the balloon times gravity. What is the total mass being supported? Mg is the density of helium. This much helium is being supported. So density of helium times volume times gravity plus mass times mass of the rubber balloon itself. Okay, so that's the weight being supported. So since a helium balloon rises, what must be true? This buoyant force is greater than this weight. Okay. And if this buoyant force is greater than that, this balloon will accelerate. It'll keep accelerating. Okay. In fact, there's an old story. This happened for real. So this retired postman, he got a one of those lounge chairs, and so here's the chair, and he tied helium balloons all around the chair. He did this. This was in LA, and he rose up into LA airspace. And so these flights that were coming in freaked out. And he had a BB gun. So why did he have a BB gun? What's that? Yeah, pop the balloons to land. And he lived to tell the story. What's that? Yeah, that's great.
That's the craziest part of the story.
What's that?
The craziest part is he survived.
Yeah. All right. So let's calculate these guys and this guy. Okay. So the buoyant force is the density of air. Density of air is 1.3 kgs per meter cube. And the volume is 2 liters. 1 liter is 10 to the minus 3 meter cube. And times 9.8. So the buoyant force is, a 2-liter balloon, the buoyant force is 1.3. And let's calculate mg, density of helium times volume times gravity. What is the density of helium? Okay, so the density of helium is 0.179 kg per meter cube. 2 into 10 to the minus 3 meter cube times 9.8 plus mass of the rubber. What was the mass of the rubber? 1.5 grams. 1.5 into 10 minus 3 kgs times 9.8. So you see the weight of the helium and the balloon is less than the buoyant force. Okay, and so the balloon will rise. The buoyant force, that difference is about 7, which is 30%. Okay. it says estimate the time it would take to fill a pool with a capacity of 80 liters using a garden hose delivering 60 liters a minute. How long would it take if you could divert a moderate-sized river flowing at 5,000 meter cube per second? Yeah. So part A, uh, so time is volume divided by flow rate, 80,000 liters divided by 60 liters per minute. Okay, so the minute will come on the top, and this is so it'll take you all day, 22.2 hours to fill the pool with a garden hose. Okay. Now, if you divert a river 80,000 liters and 1 liter is 10 to the minus 3 meter cubes per liter, and then the flow rate is 55,000 meter cube per second. So this makes that 80 meter cube divided by 5,000 meter cube per second. So if you use divert a river to fill it, then you can fill the pool in a millisecond or something like that. $16 milliseconds. Okay. So let's do one last problem. So every few years, winds in Boulder, Colorado attain sustained speeds of 45 meters per second, about 100 miles per hour. Okay? When the jet stream descends during early springs. So jet stream is these rivers of air that are flowing at 100 to 100 to 100, 200 miles an hour. Okay. Okay, so there are the jet streams. So there are the jet streams, and okay, so they're at about. They're at the height of commercial where commercial jets fly, which is about 11 kilometers. So they're that high. But if they come low, close to the ground, which happens near Boulder, then you have hurricanes type winds blowing on top of your roof. Yep. When the jet streams descend during early spring, approximately what is the force due to Bernoulli's equation on a roof having an area of 22 meters square? 220 meters square. 220 meters square is about half the size of this room. Okay, so so here's Bernoulli's equation. Pressure 1/2 rho Okay, so what Bernoulli's equation is telling you is the sum of these three terms at a given location is equal to the sum of those three terms at another location. Okay, so here's a roof, here's the room, here's the wind blowing, here's V1, the wind blowing at 100 miles an hour. What is this wind velocity here? Inside the room? 0. V2 is 0. Okay, so if this is small, this is high. Wherever the fluid is flowing faster, the pressure is lower. Okay, so the wind is blowing hard here, the pressure here is low, the pressure here is high. So there's a net upward force on the roof. Okay, so strong winds, with strong winds, the pressure inside will blow the roof up. Okay. So this force, okay, and in a plane, that's the force of the lift. Anyway, that force, okay. So for instance, at this point and this point, y1 and y2 are roughly the same, and you can cancel that, okay. And anyway, the difference in y1 and y2, that term is very small, so we can neglect that. Okay, so the force is P2 minus P1 times the area of the roof, and P2 minus P1 is, so P2 minus P1 is 1/2 rho V1 square minus V2 square times the area. And the density of air, so they give you the density of air is that. V1 is 45 meters per square times the area. Okay, that's 25,000 kgs. That is the weight of a fully loaded semi. So that's 3 school buses. Okay, so you put 3 school buses on your roof, and hopefully on the inside, and hopefully your roof won't come off. That's more dangerous than putting the 3 school buses on top of your roof, because it can withstand compressive forces. This is just the hinges have to hold against that force, and that's much harder. Yep.
So that force is upwards?
Yeah, that force is upward. So you're pushing on the roof upward with a force equal to the weight of a fully loaded semi. Yep.
Could you explain again why the lower velocity speed has a higher pressure?
So I'm going to write just 2 terms. Pressure plus 1/2 rho V square equal to constant. That's what Bernoulli's equation said. left out the other term, okay? So if this fluid is flowing faster, this term is bigger, so this has to be smaller. If this increases, this has to decrease. Hmm?
Why?
Because Mr. Bernoulli says the sum of those two has to be constant.
Oh,
Yeah.
yeah, so it doesn't.
Yeah. So we have a lot of applications with that.